Good morning. My name is Vishnuvardhan. I'm from Electrical and Electronics Engineering. My today's DC machine tech talk topic is energy efficiency optimization of torque vectoring control for battery electric vehicles. So it's simply nothing but how to increase the energy and torque in the electric battery vehicles. The introduction of electric machines as a component of vehicle powertrains is currently ongoing process. There are already many powertrains topologies on the market, which include one or two electric machines to support the internal combustion engine and numerous hybrid electric vehicles. Concept like the Toyota Virus, by utilizing the electric machine capability of recuperation and the superior energy efficiency characteristics, HEV provide an increased fuel economy compared to vehicles solely using an ICE. However, their maximum energy efficiency is still limited due to usage of an ICE as main propulsive element. A further decrease in energy consumption may be introduced by battery electric vehicles, which are purely propelled by one or more electric machines. Yet, even with their inherently superior efficiency compared to ICE-propelled vehicles, their range is restricted to around 15 to 200 kilometers for middle-class vehicles due to the limited energy density of the batteries. For, for battery electric vehicles, new powertrain topologies like the individual propulsion provides additional degree of freedom of how to generate the traction for the technique of distribution the braking force wheel individually individually provided new driving assistance system can be developed which can not only distribute braking force but also propulsion force in a vehicle individual manner. This technique is called torque vectoring and allows for an active torque generation around the central point of gravity of the vehicle. While there are plenty of research projects focusing on the improved vehicle dynamically, and almost no focus was set on the research on the improvement of energy efficiency, which supports to overcome some of the previously mentioned problems of battery electric vehicles. In addition to gain due to tire power loss reduction by yaw torque generation, it is possible to increase the energy efficiency based on a torque distribution, taking the efficiency characteristics of the electric machine into account. Hence, we hereby propose a system combining those aspects in a novel TV control system for BV. The efficiency gain for numerous driving situations is based on the following principle. Calculation of a yaw torque supporting the vehicle dynamics in a way to decrease energy losses due to wheel slips. Application of the driver demands torque by the wheel individual electric machines is an adaptive way taking their energy efficiency characteristics into account. This paper is based on the idea we presenting and provide a comprehensive exhibition of developed system with a broader view of on the results. The principle of active torque generation is utilized in many research publications to achieve a superior dynamic response of the vehicle. One possible starting point for the development of a TV control system is the dynamic normal load variations on the tires during longitudinal and lateral maneuvers. Electronic brake force distribution system already take Take this into account by shifting the braking force to the front brake pads when the normal tire load is increasing at the front axle and decreasing at the rear axle tides. The authors are extending this idea to lateral maneuvers under influence of regenerative braking. Equivalently to the braking scenario, the tire's normally loads are shifted from the inner to the outer wheels when entering a corner. This leads for the same propulsive or braking force to a higher longitudinal slip at the inner wheels and may lead to safety critical situation. The authors hence suggest using tire load sensors and distribute the generative braking force in proportion to the currently sensed tire's normal loads. It will be shown in the course of this document that this idea, while leading to good results during braking maneuvers as intended by the authors, cannot be simply extended to the acceleration case or steady state circular driving maneuvers. In this situation, unacceptable oversteering behavior is introduced when solely relying on the normal load propulsion distribution. The authors are using PI controllers to control the lateral acceleration and the yaw rate independently while also focusing on improved cornering dynamics. Other publications are researching possible T-way track statistics based on the linear quadratic regulators. Both publications are proposing a combination of reference model, feed-forward control, and feedback control based on NQR. Reference model and feedback controller are very similar in the given citation, only the feed-forward part differs significantly. Since is using a flatness-based feed-forward while is using a proportional feed-forward. The majority of research suggests using a linear single-track model as reference since it is known to be behavior the driver is assuming for the vehicle. Besides the mentioned approach to improve vehicle dynamics, there are some publications which are explicitly focusing on the energy consumption during cornering manual. The authors of the analytically and experimentally evaluate the effect of active yaw torque generation by in-vehicle motors. They showed that for the steady-state cornering cases evaluated in their experiment, only slightly more power is required to support the engine dynamics by an active yaw torque. The paper processes both an LQR control similar to an accidentally a proportional controller to directly control the yaw rate. Both approaches are compared in terms of vehicle dynamic behavior and energy consumption and provide promising results. While the recuperation of the electric machines is utilized in the approach, the efficiency characteristics of the machines are not considered specifically aims at increasing the efficiency of an electric vehicle with excellent individual machines and T and TV differentials during cornering maneuvers. They utilize the type normal load proportional approach introduced in and combine it with an optimization based on the electric machines and the differential characteristics to generate the torque on each way. Each week they use an offline optimization based on a vehicle dynamic model and the powertrain characteristics. In contrast to the topology in vehicle, individual machines introduce the degree of freedom to disengage each vehicle separately. It is shown that significant energy benefit can be achieved by disengaging one or more machines in certain operating conditions. Hence, a wheel individually propelled topology offers superior energy saving potential if a meaningful operation strategy is found in an LQR is proposing, taking the electric machine efficiency character into the performance function. Due to the linearization of the nonlinear efficiency property, the optimization can only take the ohmic losses in the stator winding into account while mechanical friction and the inverter's losses are not addressed. In the contract to that, our approach utilizes knowledge of electric machine efficiency as well as the electric dynamic model to reduce energy consumption. By declutching some of the electric machine, their energy efficiency can be improved also for manuals with low or no lateral accelerations. Vehicle model in this paper a TV control is derived considering combined losses caused by powertrain and vehicle dynamics by optimizing the reference value on the torque allocation to the wheels. Energy consumption will be reduced. In order to develop this control system, requires knowledge of the vehicle's relevant components and the vehicle's dynamic behavior is required. Besides the vehicle dynamic models, which are not introduced in the subsequent paragraph, the energy efficiency characteristics of the installed electric machines and the inverters are of major importance. The vehicle model considered includes vehicle individual electric machine whose characteristics are displayed in detail. The four-wheel model, when looking at a wheel individually propelled vehicle, is dynamic or influenced through five control variables set by the driver and other controller. Following the driver's request, the front wheel steering angle V, which is controlled via fixed transition by the steering wheel and the wheel individual. Proportional braking forces. Thus, the subscripts L and S denote the longitudinal axis and respectively lateral axis of the tire coordinate system, which is rotated by the angle D with respect to the vehicle fixed coordinate system, spanned by unit vector and longitudinal and lateral velocity. Here in the four-wheel model, also known as two-track model, shown in figure and exhibit the vehicle's system set upon with three states: the vehicle velocity V, the vehicle's side slip angle V, the vehicle VR rate V is defined as the angle between the vehicle's velocity V and the longitudinal axis of the vehicle X. The yaw rate is the turning rate of the vehicle fixed coordinate frame with respect to the world's reference frame. Parameters include influencing the four-wheel model of vehicle mass and its inertia along the yaw axis. The vehicle base I consisting of the distance lie between front axle, rear axle, and the vehicle's center of gravity. The highest edge of these usually are made by the track. Additionally, the driving distance is relevant to parameters illustrated differently can be found. Inclusion represented an overall vectoring controlling system improving both vehicle dynamics and energy efficiency. The controller's reference generator is based on energy efficiency optimization considering a detailed four-wheel model which minimize the losses in the wheels due to wheel slip. The desired setup point is followed by an LQR through requesting an optimized yaw torque. The required torque is generated by the individual electric machine being allocated by an efficiency heuristic subsequent to the LQR. The combined system shows energy consumption benefits of up to 8.7 in typical rural scenarios with low lateral acceleration. It can achieve up to 14% energy saving. The same lap times driving a racing circuit in simulation with the industry standard vehicles dynamic simulation tool IPS car maker. Summarizing the achieved efficiency gain for highly dynamic maneuvers is due to the yaw torque control and the first flow lateral acceleration is due to the proposed disengaging of machines in partial load condition. Further work targets the behavior of the purpose and low surface. Thank you.